Hello and welcome back to Calculus 2, section 8.4 with another 3 tests, which means we will be halfway through the tests at the end of the lesson. I'm not sure if we're going to finish everything, but let's try. The first test is divergence test, also known as the nth term test in other books. And this test is extremely powerful, extremely easy, but it works only for divergence. It can only show divergence. And if you look at the chart that I distributed to all, please observe that the convergence box is completely empty. That means that this particular test is incapable of spotting convergence. So it will either say it diverges or I don't know, right? That's technically how the test works. So the divergence test so here we go. It's a theorem. It says, if summation of AK, oh wait, hold on, no, we don't want this one part. No. This is the only thing I want to write. If the limit of an as n goes to infinity is different than 0, then summation of an diverges. That's all I want to write. That's it. So divergence test says that when you take the limit of the sequence, right? Sequence. If that limit is different than 0, you have a divergent series. So one more time, series is the sum of the sequence. So within every series, there is a sequence, right? So when you write summation an, the entire thing is series, and the little an inside is sequence. So you strip off the summation part, which takes out all the addition, and you're left with a list of numbers. You take the limit of that list if it's different than 0. So if you get infinity, it diverges. If you get negative infinity, it diverges. If you get 7, it diverges. If you get 0, we don't know. All right? We don't know if you get 0. We don't know if it diverges or converges. But if you get anything but 0, it definitely diverges. So here are the examples. Summation 1 to infinity for n. You will immediately pick that an is n, and you would hit it with the limit. You would get infinity, which is clearly different than 0, diverges. Done. You might have a series 3 to infinity of n squared plus 1 over 3n squared minus 9. Your an is n squared plus 1 over 3n squared minus 9. You immediately hit that with the limit n goes to infinity, n squared plus 1. What do we know about this limit? It will be 1/3, which is not 0, divergent, boom, done. You have the series of 3 to the k from 0 to infinity. What do we do? What do we do?
Free k ln is 3.
So what's AK?
AK equals 3k.
3 to the k, and what's the limit?
ln
Limit, not ln. Okay. Okay. What do we get?
Goes to 0.
No, 3 to the infinity is
Infinity.
infinity. Yep. So boom, diverges. Or Maha? Yeah. This is geometric series. But we also see that it diverges by geometric series as well. Some problems can be done in more than one way. So, or geometric, r equals 3, bigger than 1, divergence, right? So, this is it. If you are able to take the limit, if it's not 0, right, that's it. Now, here's the next one. Summation 1 to infinity of 1 over n. So now an is 1 over n, limit n goes to infinity of 1 over n is 0. So what now?
It equals 0. And converges.
Nope. 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 It's not convergent.
It is diverged.
Yeah, but our test says that if it's not 0, it diverges. So this is where you write in big fat letters, test is inconclusive. You cannot use this test on this problem. Such is life. All right? So test is inconclusive. Can't write SI. There we go. So test is inconclusive. You got 0. Do not claim convergence using divergence test. That's like telling to someone that they're fat because they're skinny. Makes no sense. Right?
You do this test and you get 0 like that.
You have to use something else.
So can you say at that point it diverges, or I mean it's convergent, like definitely convergent,
Hell no.
or it can still diverge even though
This is divergent series and the test was inconclusive. So you will see this is called harmonic series, and in 15 minutes I'm going to prove using integral test that this is divergent. However, divergent test did not pick it up because the limit of the sequence within is 0. So anytime you get 0, you have to use something else. If you get anything but 0, it's definitely divergent. That's how the test works. It's a little bit tricky there, so pay attention, and when you see the empty box, right, that means can't use that particular test.
So basically this is just like your jam, just like throwing it out there.
This, when you get your exam,
Yeah.
well, if you get your exam, because you might vote not to have it, and you look at 10, 15 of these guys on the test, you run each single problem through this. And you might knock out 1 or 2, right? And then the rest, telescoping, integral test, right? That's how it's gonna go.
And that's basically how the entire test is going to run through all this material.
Yep, and technically that's how your chapter 7 exam was for integrals. Hopefully you went by parts. No, sorry, the USUB, and it worked in 2, right? 2 spots USUB worked. So that's the same thing. Divergence test every problem, and then whatever you get an equals 0, well, that's where you have to use something else. If you get anything but 0, diverges, you're done. Integral test. Welcome to integral test. 6. So for the integral test, you will have to do 3 proofs before you are allowed to start working on an integral test. Each one of these problems is 1 to 2 pages long, has paragraphs of writing and stuff. So let's go.
Oh wow! I remember when you showed this one to us.
Yes, that's the one.
That same smile.
Welcome. Welcome to that particular section. So all you remember is the 3 paragraphs of text, right? And then another half-page calculation, and then at the end, it converges, yay! All right, we still have no clue where it converges to, but we got the convergence.
Would this test be on the exam and
Yep.
all, even if it's very that long?
It is long, and we'll see how it's systematic, but it is integral test, it's important. So, yep, now let's go. Guys, suppose f is continuous, positive, and decreasing. For x larger or equal than 1. Then summation ak, k goes from 1 to infinity, and integral 1 to infinity f of x dx either both converge or both diverge. There's your integral test. So, where are the 3 proofs? You will get AK, which is n plus 1, let's say. You make that into x plus 1. You need to show that x plus 1 is continuous. Yay, it's polynomial, so it is continuous. That it's positive. Well, x's are all 1 and more. When you add 1 more, it's all positive. Cool. Decreasing. Not decreasing. Can't use integral test, right? For x plus 1. So these 3 proofs have to be done every time for every single problem to make sure that the results for both are the same. Because again, this is what we can do, this is what we can't do. So the only time when they both converge or both diverge is when these 3 conditions are satisfied. If any of the 3 conditions fails,
Everything fails.
well, you can still compute it, but there is no guarantee that if you get convergence here, that converges, right? So if these 3 conditions are satisfied, these 2 must do the same thing, okay? That's the trick. So you have to prove these guys every problem, and that's where the chunk of the work is. And then the next chunk of the work is to do the improper integral of type 1. And then after that, you can claim if that integral converges, that converges. If that integral diverges, that diverges. This integral might converge to a half. This will not converge to that half. This converges to something else. It's just the integral did. So you can't, only the geometric and telescoping tell us the answer. Converges to 2, converges to 7. All the other tests, if you figure out convergence, you don't know what it converges to. So when integral converges to 7, your summation also converges, but to some other number, not to 7. So we'll be a little bit careful with that. But other than that, let's crank the summation 1 to infinity, 1 over n, known as harmonic series. Important series, has a name. So here is what I'm going to do. I need to prove the 3 parts. Number 1, is it continuous? I'm looking at f of x equal 1 over x. Now, before you jump and scream no, because at 0 we have vertical asymptote, I will remind you that you are on a restricted domain x bigger than 1. So, because this function is so easy, and you know its graph, values 1 and on are here, and it's clearly continuous on this. But let's say your graph is not available. How do you do it? Well, you take the derivative. To show that something is decreasing in Calculus 1, you take the derivative, and if the derivative is negative everywhere in that interval, that means that the original function is decreasing everywhere on that interval. So I'm going to do this right way, even though we already know the answer, because it's easy function. I will take the derivative, the first derivative. I will get negative 1 over x squared. And I will simply say for x bigger than 1, I always have a negative number divided by positive number, which is always negative. Therefore, it's decreasing. We know from Calc 1 that negative first derivative says decrease. So decreasing is proved. You can prove decreasing either through showing that the next term is smaller than the previous term, or you can do the derivative. I like to do the derivative because it's simple. 2. So continuous, is it positive? Oh, wait. Change the continuous into decreasing. God damn it. All right, decreasing. Continuous. Is it continuous? How do we deal with continuity? Look what I have. I have a function on top, which is 1. That's a constant function. On the bottom, x. Also, continuous polynomial. When you divide two continuous polynomials, as long as the denominator is never 0, and it can't because x must be bigger than 1, we have continuous function. So over here, we use theorem from Calc 1, which states that all polynomials are continuous on the entire domain. Yes, you are writing sentences and paragraphs. So the quotient, this is another theorem, of two continuous functions is a continuous function provided that the denominator is different than 0. Now in our case, I have 1 divided by x, but x is bigger than 1, so this is 1 over 1, 1 over 2, 1 over 3. It's never 1 over 0. Therefore, continuous. I have two continuous functions divided. What other functions are continuous? Exponential, logarithmic, square root, they're all continuous.
How can you tell they're both continuous because they're going from negative infinity and positive infinity?
No, we are only going from 1 to positive infinity. But the way I can tell is I know the theorem from Calc 1, which says that all polynomials are continuous, and these two guys are polynomials.
Okay.
So polynomial divided by polynomial is continuous as long as the denominator is never 0. That's where the x bigger than 1 helps. So that works down. The only thing that is left is positive. That's number 3. Is it positive? Of course it's positive because we have f of x equals 1 over x. For x is bigger than 1, you have positive divided by positive, which is positive. So we have the positive also checked out. Yeah, we can do the problem now. because we proved all three conditions. So, since all three conditions hold, it's positive, it's decreasing, and it's continuous, we can do integral 1 to infinity of 1 over x dx. What's the integral of this?
1.
Hold on. Limit first, and then you tell me what the integral is. What do we have?
0.
What's the integral of 1 over x?
ln x.
That's much better. ln x from 1 to b, which is, don't forget these limits. Poor Calc 1s, they did the limit definition. 2 students, 5 steps, didn't put limit. ln b minus ln 1. How much is ln 1?
0.
Boom. Now, how much is ln of infinity?
Infinity.
So what does that mean for this integral?
It goes infinity.
So what does that mean for the integral? Is it convergent or divergent? Diverges. Boom. Now, guys, here we go. Here is your answer to the question. This is, I'll do it red. Answer. This is what you write at the end of the problem. Answer says, since all three conditions hold, and integral 1 to infinity 1 over x dx diverges, series summation 1 to infinity 1 over n diverges by integral test. That's where you, this is where you get your points. This is your answer to the question. This is what you box. This is where the box goes. So welcome to the first simple example. Welcome to the integral test. So we do 3 proofs to first show that we can do integral test. Then we crank the improper integral to get converge or diverge. And then we simply, with this statement, claim that because integral diverged, series diverges. So proofs allow us to do the integral and make the link between the two. If the 3 proofs hold, both integral and series converge together or diverge together. You will recognize integral test when you see stuff that you can integrate by u sub, by partial fractions, by trig sub, by parts, by chapter 7. Okay? So when you see a form of a problem that you can integrate and then those 3 conditions hold, you unleash integral test. So now this proof was done to show that harmonic series is divergent. It looks like it should converge, right? 1 over n. It's so nice. But it doesn't. It actually diverges. And we also seen that divergence test did not detect that because the limit of the sequence was 0. The next order of business is what's happening with 1 over n squared. Is that going to converge or diverge? That's the question. So there's nothing else left for us than to repeat the whole procedure from scratch.
It's a really good thing I already lost my mind before this, because now throwing a reason out is that I don't have to do anything. What are they doing?
Summation of 1 over, hold on, the comparison is coming. So we have 1 over n squared, where the function will clearly be 1 over x squared, the continuous analog. Remember how the graphs graph the same, right? One has dots, the other one has continuous line, but they go through the same dots. So that's why you are making this comparison between the two, because you can't integrate, well, you can, but it's graduate school, a big integration for the discrete stuff. You are looking there, and you're making a continuous function, and then you are making the analog between two worlds. So now what we want to do is run 3 tests. Now, for the most part, if you know what the graph looks like, you are done. You don't have to write the essays. On the other case, when you don't know how the graphs look like, you have to do derivatives and all of this stuff. So you know how this graph looks like. It's the graph that goes like this, right? That's how it looks like. And this is where 1 is. So if you look at this part of the graph over here, which is the part of the graph that you're interested in, from 1 to infinity, why 1 to infinity? Limits on the sum are 1 to infinity. So the domain for this 1 to infinity. When the limits over here are 15 to infinity, your domain for the f of x becomes 15 to infinity. So now you are looking at this. You're looking at this problem, and you look at that little part of the line over there. You see it's decreasing. You see it's always above x-axis, so it's always positive. You see it's continuous because discontinuity is 0, and that's not in the domain. So again, we could have used this before, right, as well, but I wanted to show you the process for all the proofs as well when you can't use it. So decreasing, check. Positive, it's above x-axis, always, check. And the decrease positive continuous, right, discontinuity at 0 is check. Now go ahead for practice, write out the paragraphs to, to fill in the blanks.
May I ask you, so basically drawing out a graph which helps show that it is decreasing, make it positive, and continuous.
It's enough to prove, but most of the time we don't know how graphs looks like, and then you would have to go through you remember the 4.3 in Calc 1 where you are graphing a function for 25 minutes? That's the alternative. If you don't want to do those 3 proofs, you don't have a graphing calculator, then it's going to be 25 minutes of cranking Calc 1 13-point calculation to graph a function by hand. So few theorems for continuity and stuff should be good, better. All right, so now since the conditions are satisfied, I'm going to set up my integral, improper integral from 1 to infinity of 1 over x squared dx, which works out with the limit b goes to infinity, integral 1 to b of x to the minus 2 dx, and then that integrates into x to the minus 1 over minus 1, so that's negative 1 over x from 1 to b. That is the limit b goes to infinity of negative 1 over b minus, and minus make a plus 1 over 1, and we get 1 in this case. Like 1 over b would be 1 over infinity, which is 0. 0 plus 1 is 1. So the integral converges. Answer. Time to write the answer. Since 3 conditions hold and integral 1 to infinity 1 over x squared dx converges, the series summation 1 over n squared 1 to infinity converges by integral test.
May I ask you, so should we write out 3 paragraphs on like the answer to show on the exam to show that it's positive, decreasing,
Yes, it's either the 3 paragraphs or you know how the graph looks like, and then you can just point on the graph it's decreasing, right? So it's one or the other. You have to have something, right? So, guys, what's next? Well, clearly 1 over x cubed, right? And then after that, immediately we have 1 over x to the 4th and 1 over x to the 5th. But don't forget that in between 4th and 5th, there is also 4.1 and 4.19 and 4.27, right? So there is a little bit summary. And the summary for that is called P-series. Summation of 1 over n to the p, where p is that exponent when the harmonic series was 1. In the second example I did was 2. And then if you want to go and do 3, right? And so on. So P-series looks like this. And you have it on your sheet, right? I should be doing this in red. I just realized that I'm using black on this. So 1 over n to the p. So if p is less or equal than 1, we have divergence. If p is bigger than 1, we have convergence. So now you don't have to crank integral test for basic ones. It's called P-series. And you want to start this test because you are going to use a lot of it in comparison. So 8.5 limit comparison test and the limit comparison test are going to use this a lot. It's like a fallback, right? You have the method that transforms your integral and then you can finish it off with a u sub. Technically, that's going to be like this. The comparison test and limit comparison test and direct comparison test are going to do something to a problem, and this will be used in between. So P-series. Now, P-series is easy to use, right? So far, you have 2 annoying ones, like telescoping, right, forever, and then integral, insane, right? Geometric, easy. Divergence, easy. And P-series, here we go. Summation of 6 over n to the 3 from 1 to infinity. What do we have there? What do you say? Yeah, what do you write? You have to do something. Well, first write p equals to 3, bigger than 1, converges by P-series. Yeah, that's it. That's how you do P-series. Of course, it's math.
Of course, it's fabulous.
Yeah. That's all I have to say on P-series. We're going back to integral test. Well, no, we just did integral test to kind of scratch the surface and use the P-series part, get that out of the way, and now we go back and do actual problems for integral test. Tan taran tan. Tan 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 tan. This is a cool one. In my opinion, my humble opinion. Problem 23. Summation of 1 over square root of k plus 8 from 0 to infinity. So, integral test. Now, how do I know it's integral test? Well, it has u sub written all over it, right? U is k plus, well, x plus 8, right? And the problem is a joke. But then, don't forget the 3 rules we have to prove in order for that stuff to work out. Now, here is another thing, guys. I look at this problem, and I know it diverges just because I'm divine, right? At some point, this will click so well not during the class, obviously, like when after differential equations, let's say, that you're going to look at this problem, you're going to say, oh, look at that, 1 over k to 1/2. So p is 1/2. That's less than, right, by comparison, this has to, right? But it takes time to get there. Like, it didn't make any sense to me when I was taking stuff. So all I know now is I'm looking at this and I see integral test because k plus 8, which is x plus 8, I can do u sub. So let me run through 3 proofs and make sure that the integral test actually can be done, right? So what do? We start with first creating the function, which is 1 over square root of k, x plus 8, x plus 8. That's the first thing we do. And then we say positive. Of course it's positive. Square root always gives the positive number, right? So positive divided by a positive is always a positive. We're good there. Again, answers to every square root is always a positive value. Think about the graph of the square root, right? All the y's are positive for it.
But it has to be greater than like 0.
Yeah, for greater than 0. Yes. Okay, maybe you should write that here. 0 to infinity. Write the domain. Fine. Is it continuous? Hell yes, because we know that 1 is constant, therefore continuous. And then you have a composition of 2 continuous functions is continuous. So I'll write this and just say composition of 2 continuous functions is continuous. That's a theorem in Calc 1, 2.6 section on continuity. The theorem that polynomials are continuous, square root is continuous, ln is continuous, e to the x is continuous, sine and cosine are continuous. That theorem is 2.6. Also it says addition of continuous functions, subtraction of continuous functions, multiplication of continuous functions. All of them are continuous. And it also has a theorem that says that the function composition, when you plug one function into another function, is continuous, provided that the both functions you are composing are continuous. Now, the theorem says root x is continuous. The theorem says x plus 8 is continuous. When you plug one into another, the composition is continuous. So we have now division of 2 continuous functions. Denominator cannot be 0. So division or quotient of 2 continuous function is continuous given denominator is different than 0, but our denominator is at least 8, root 8, right? We have denominator always bigger than root 8, so can't be 0. Therefore, continuity, done. And the last one is decreasing. Our function f of x is, I forgot, 1 over root. We are going to hit this with the derivative. We are getting 1 over 2 root x plus 8.
How can I be negative?
Uh-huh. You see why I left this for last? I wanted to go through the other pane just for practice. Can't use the method. Walk away.
What's that evil laugh coming from?
Such is life. So, yep. Welcome to level 7.
So there should be like a negative 1/2.
Exactly. It has to be a negative somewhere, right?
I forgot the negative.
Well, it's negative 1/2 is the root and denominator, right? So
No, I meant the negative 1/2 in front.
there's no negative 1/2 in
So
plus
it's
1.
like x plus by 8.
Oh wait, this is in denominator. It is negative. Ah, it's in the yeah. No, this is good. Ah, this is not. Where's the troll question? Yeah, I know. No, there is a troll question here. I don't remember which one it is now. That's fine. All right, let's do it. Let's do it. Hold on. Rewrite this first. Rewrite this as. Oh, you missed it, man. Well, you watched the stream. You will have to watch the stream. So negative 1/2 x plus 8 to the negative 3/2, which can be written as negative 1 over 2 times x plus 8 to the 3/2. There we go. So this is always negative. This is always positive. Therefore, negative divided by positive is always negative. So decreasing. Boom. All right. Cool.
Still prove that it's still increasing if they're both positive as well.
No, it has to be negative derivative for decreasing.
Okay.
So now all three conditions hold. Therefore, integral 1 to infinity 1 over x plus 8 square root dx u sub and the rest. So u is equal x plus 8, du is equal to dx. Plug everything in. We have the limit. B goes to infinity. Integral. Plug in 1 over there is going to be a 9 to b. And then we switch the limits, right? And then we have the stuff, which is u to the negative 1/2 du, which is negative 1/2. So plus 1/2. So it's 1/2. So it's 2 root u. So limit b goes to infinity 2 root u from 9 to infinity. Then we got divergence as I promised. Limit. I say b, not infinity. So limit b goes to infinity of 2 root b minus 2 root 9, which is not important because it's infinity, and there we go. And then you get to write the answer. Since 3 conditions hold and integral 1 to infinity 1 over square root of x plus a dx diverges, the series summation 1 to infinity of something 1 over k plus 8 diverges by integral test. Where's the troll question? I'm sad now.
Well, number 42.
That's also u sub. Right? You see the k squared?
U equals, yeah.
Without k would be partial. Would be integration by parts, right? Ooh.
looked at this and it's from
2 minutes. I know. No, we said we go to 3, right? 3 a.m. We're not going home. What are we gonna do home? This is where the stuff happens. Look at these walls. The school was locked. School was locked 22 minutes ago. All right. All the doors are locked. No one can come in. We're safe. We have electricity, and there's running water over there. What happened to the bag of chips that was floating around? We have some food. We're good till 3, 4 a.m., guys. We can ration, all right? It's okay. Tan 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 tan. Yep. So
Is there evil laugh?
no time yet. This is it's brewing.
You want to solve this?
So, oh yeah, the solution for this is 2 steps. You're looking at this and you immediately are thinking all the worse because you're mixing the polynomial function with the transcendental function, which in the integral world means integration by parts. You're seeing k squared. Like, you know that the derivative will not kill sine k. You also know that the sine k does this. That's definitely going to ruin the decreasing and increasing part, right? So this clearly doesn't look like the integral test. But it's so damn close, right? One big part that you need to understand and learn for this chapter is that sine and cosine are bounded by 1. So this problem is bounded by 1 over k squared and by p series that converges. We're done. That's this problem. P series. So I'm going to write this in blood over here. Absolute sine k is bounded by 1. You can replace it by 1 because it can't be more than 1. The most it can be is 1. And if it's 0, does it contribute to the sum? So we don't care, right? So I'm going to replace every sine and cosine x, n, k, whatever it is, with 1. Because it cannot contribute to the sum. It's either adding 1 or it's adding 0 or anything in between. Does it make sense? So I replace it by the most it can be. That's why we say sine k is bounded by 1, cosine k is bounded by 1. So for the most part, you get to ignore them. You get to replace it by 1. And that's that. So the other ones, no. Tangent goes to infinity at pi over 2. So that...
Oh, well, I meant with sine and cosine. Is there ever a time where we can't just ignore them?
Yes. There is a part that we are going to cover in section 8.6 on alternating. You already seen this last class where I gave you that the cosine n pi is the same as minus 1 to the n. This term here creates alternating series, which triggers a completely different situation. So cosine n pi and also sine of pi n pi over 2, right? Because that one also would play 1, negative 1, 1, negative 1. So those two guys, so sine n pi over 2, will also give you this kind of term. Actually, plus 1 in this case, right? Because sine of pi over 2 gives you a positive, so at 0... Oh, no, it was good. No, for 0... For 1. pi over 2 is positive. So yeah, I was right. Either plus 1 or minus 1. So if you get anything else other than these guys, you just ignore sine and cosine, because it's like equal to 1, and then you do times 1, doesn't do anything to it. So this problem that looked really bad is actually just a p-series done by using your eyes. Guys, we covered half of the sheet, right? We covered half of this sheet on next week. So that means lab, right? Lab 4. There we go. So we took.
3 is the other chapter 7.
Yeah, 3 is still chapter 7. No, I don't know. I'm just saying the lab 4 is up. That's all. We're half through lab 4. Bye, stream.